So can I ask Megan Becker to please come up to start us on operationalizing geometallurgy, and she'll be followed by Jeremy Mann and Robert Schauscher.
Right, good morning, everyone. It's my pleasure to be here today and also to be working with Adjunct Professor Robert Schauscher and Adjunct Professor Jeremy Mann. And we've been looking at setting up a project. It's quite a large collaborative project, and it's called Operational Geometallurgy. But I just want to give you some of the flavor of what and where geometallurgy is before we even go into looking at it in terms of an operational context. So to start with, I just want to reflect on some of the challenges. We've looked at many in the sustainability space in terms of the social side, but in this project, we've really zooming in on the environmental and the techno-economic challenges. And you keep hearing questions, most people like to start their presentation, we got much lower ore grades, and the ores are much more complicated, they're harder, they're further, deeper, more remote. And that is the challenge in the techno-economic space that the mining industry is having to deal with. We've got these ores, these are the ores we have to process. We have to process them the best we can and get the most value out of them. So we also hear this thing called ore variability, this word being used a lot. And this quote captures it quite nicely. And what it says, neither geologists, mining engineers, nor metallurgists can change the fact that all deposits are zoned with respect to metal grades, mineralogy, mineral abundances, mineral textures, and other parameters such as physical hardness, all of which impact on the treatment costs and recovery of metals as an ore deposit if progressively mined and depleted. So now I'm going to take you back a little bit to geology lesson in terms of where does the ore variability actually come from? Why is it there? So we're going to go zoom across to South America and just zoom in on a porphyry copper deposit. The porphyry copper deposits represent 2/3 of the world's copper production. So there are massive deposits in providing millions of tons of copper and molybdenum, metals like that. But essentially, you've got an ore that is formed as a result of magmatic processes, things like magmas and volcanoes. And part of the magma, there is a hydrothermal fluid. So the fluid's not officially part of the magma. And the fluid also has a lot of vapor in it. And what happens when your magma and this fluid starts getting to the surface, you get depressurization. This fluid then escapes, moving towards the surface. And as it depressurizes, it's carrying a lot of force with it. Essentially, it starts hydrofracturing. And it fractures this entire network through your rock mass, from which then these fluids can move. And that's sort of really how porphyries are forming. That's the mechanism how these fluids get into the rock mass, and then they will start mineralizing and depositing your copper and your metal, and sometimes gold, copper and molybdenum, and sometimes gold alongside them. One of the other very common or signature characteristic of these porphyry ores is that you also have different zones of alteration. As these fluids are interacting with the rock mass, they have different signatures. And in this, we've just got 4 different zones titled potassic, cericitic, propylitic, and argillic. Each 4 of those zones has characteristic signatures on alteration. Now, this is a really nice ideal diagram. In reality, the rocks don't behave like this. The rules, you'll have zones of argillic, nothing's nicely symmetrical, it's all over the place. That's the ore that we're processing. What does it do? So this is a nice concept from a paper of, in fact, one of Dee's students she's worked with, and basically he's looked at the different types of alteration listed here. I don't know that you can necessarily read them with different photographs, but basically he's capturing that each different alteration type has a different effect on the mill throughput, flotation recovery. We could extend it in terms of acid rock drainage potential, how hard the rock is. So that's what we're trying to capture when we talk about ore variability. Right. So how do we do this? We have this lovely big word called geometallurgy. Basically, it's a tool that we're using to be able to capture this ore variability and to be able to manage it. We want to manage it and be able to get the most value out of it. Not that we're completely on the back foot and, oh, the ore is different today from yesterday. We want to be able to use the variability to our advantage in terms of getting the most value out of that ore. So now, one of the ways in which geometallurgy is represented is this thing called the block model. Block model is a three-dimensional model of different granularity that captures the properties of the rock in 3 dimensions. So this is an open pit from a porphyry copper deposit in Chile, and every different color or every little block represents a unit of ore, X many meters or something, volume. Each different color represents something about the bond work index. So they've mapped characteristics about the breakage and the hardness of the ore right through this entire deposit. This then allows them the ability to be able to plan what do they want to mine when. So in this case study, which was actually presented in Perth earlier this year, they then went further in terms of quantifying the value, and that's what I will also look at. So let's just look at some definitions of what geometallurgy is. We've got one that really says it's about maximizing the net present value of the ore body while minimizing technical and operational risk. It's about the money side. There's also the ability to tailor mining and mineral processing development and operational options more closely to the characteristics of the ore. Lower costs, improved recoveries, and fewer project failures. And then the one that I tend to use is like, it's a holistic approach to managing ore variability, allowing us to get the maximum value out. And we've also put here, it's incorporating all relevant aspects of ore body knowledge. There is a huge amount of ore body knowledge out there. Not necessarily all of it is relevant, and some will be relevant in one deposit and not relevant in another. And that's really where it gets interesting, I guess. So why do we do this? In terms of the prize, some people actually tried to put a financial value to it. There's a paper from 2014, McFarlane and Williams. They did a geometallurgy approach in terms of the design of a plant in the copper belt, and they said that there are $127 million improvement in the NPV using this geomet approach. This other case study of the porphyry, which I showed you, the block model, they have also then, here's some graphs of the sulfide and oxide copper equivalent production. They had more, 1.4% more metal produced, 13% more the value, and also it really allows them to be able to understand the cash flow much better, optimize the cash flow for what they need in the ore. All right, so how do we go about doing this? The ideal approach, and I very much said ideal because there's no such thing really as ideal. Everyone tackles it differently, but ideally we want to get information about the ore on different granularity scales. We want information about blasting, crushing, grinding, liberation, recovery potential, environmental indicators, things like, is this material going to be acid forming or not, acid consumption if you're looking at a leaching circuit, and you want that information throughout the ore body. That information is then embedded into the 3D block model, and from that they also are able to domain the information. So they'll say, I've got domains of ore, which are areas where your blocks will have similar characteristics in terms of any one parameter that we're interested in. Then, once we've built this model, we want to actually use it. And that way it gets more interesting, because now we want to use it in terms of mine planning. Making sure that the ore that goes through to the plant, or in terms of the environmental, being able to tailor the characteristics so that we can process it to get the best value out of it. Once this is done, it's also about going back and saying, did I mine what I said I was going to mine on a space and time location? And also, did I get value out of that block as we said so? So if we assumed we were going to get 80% recovery out of that block of ore, did we actually get 80% recovery? And if not, why not? Then go back and put that information back into the block model. So that's the ideal approach. Then it's also about embedding this into the culture of the mine, that everyone in the site buys into this and uses this information in terms of the operating. So then, in every ideal concept, there's a but. People have been working on this for quite a few decades, and there has been a lot of success. But it's predominantly been in exploration, pre-feasibility, and feasibility studies. And I guess one of the major things is being able to have better spatial models that allow them to convert their resources to reserves. And also, when they do the resource to reserve conversions, they traditionally have these things called modifying factors. But now they have information on actually the response variables of the ore. So how is the ore actually going to behave in this context? Not, I'm going to take a fudge factor and use it as this. We actually have better knowledge. And from that, they are able to put more competent statements out in terms of what they report in international reporting on your SAMREC and your JORC codes, mining codes. So then the but comes. It's been used in these pre-feasibility and feasibility stages, but why hasn't it been used as an operational stage? Why are people not actually using it on the day-to-day running? And that's really just what I want to focus a little bit about. The mining industry as a whole, it's a huge industry, and it employs people from many, many different disciplines. We've got geologists, we've got statisticians, mining engineers, metallurgists, environmental engineers, human resource people. We've got a huge range of people bringing different skills. And often on a mine site, you'll find that they're working in different departments that you physically have to get in the car to drive from one department to the next. You can't just walk across. So you've got silos that are divisional silos in terms of the way they think, but also they're physical silos because the communication isn't necessarily easy for them to have. Geomet is the geo and the mets. There's no geomine met, and traditionally in many of the geometallurgy conferences, the mining engineers have just not been present. So now we're questioning, where are the mining engineers and why aren't they in this discussion? Then supposedly we've also seen very little involvement from the operational decision makers. The people right at the top buying into this concept and putting the conversations there so that this Geomet approach will succeed, and the Geomet is supported right through the company, and everyone sees the value in terms of the Geomet project. And then also, we often see that between different disciplines, they have very different production metrics. So the miners are billeted in the sense on the tons the material they send to the plant. Whereas your metallurgists will be, their points score essentially come from the metal they produce or the amount of concentrate they produce in the grade. Whereas the miners can just send ore, or supposedly ore, to the plant. When they're running a bit low, they might just put a bit of waste in because now they're making their tons. So they're delivering what they need to, but it's not necessarily the right value. So we've seen advances at the scientific and systems level and not at the pragmatic day-to-day operational level. And then also just a variety of jargons. And I think that's one of the lovely spaces of working in minerals to metals, working in transdisciplinary and cross-disciplinary. We have to learn what each other's jargons mean. We have to learn not to use the jargon so much. And this comic really just sort of gives an indication of different jargon. In the context, the geologist sees something, he says he's interested in sulfate, sulfide, saying, okay, which mineral is it? What mineral am I dealing with? The resource modeler just wants to give it a number. He just wants to put a number and he can put it into his block model. The operations engineer just knows that it's a yellow rock, it's a red rock, it's a gray rock. They know the red rock's good, the gray rock's bad, something like that. And then the metallurgist now is like, okay, it's all in terms of ratios of acid-soluble copper or acid-insoluble copper, and they want to know what's going to happen in the plant. So everyone's looking at the rock with different parameters of the rock, but they're looking at it with different things in mind, and it's being able to understand why they're all seeing it that way. So where we've got to, we're about to launch a project called Operational Geometallurgy through Amira. We have gone through the expression of interest. We're now in the proposal development stage, and we are looking at creating a practical decision-making framework which allows us to implement geometallurgy on-site. We're very much looking at the operational space, looking at the short to medium term in being able to help mining operations, specifically in the climate we're in today, to be able to manage the ore feed variability so they can get the best value out the ore. It's not only about grade or metal, it's value, and also and managing this variability right across all the activities of the mining operation. So for the metallurgists, we like to have these little graphs, sometimes called control charts. Basically, they want to move from something on the left, which is unstable, where, say, this is feed to the plant, it's varying huge perturbations on the scale, to stable, to capable, where you've got very few fluctuations, and they're able to manage the ore variability, and not just manage it in terms of, okay, I can cope with it, but actually I can use it to my advantage to be able to get the most value out of the ore. And that's the project that we're going to be looking at. So yes, thank you.